So just to give a quick introduction to those who are not familiar with Trellis yet. So Trellis is a production-ready multi-purpose leaf-spine fabric. It's built based on three major concepts: open source software, white box hardware, and of course it's SDN based, and it's powered by our ONF SDN controller. So as you can see here, this is a typical topology of Trellis. You can see a leaf spine fabric in the middle. At the bottom, you can see you can attach compute nodes on which you can run VNFs and your services. You can also attach a few access devices that further connect to your subscribers. And on the right-hand side, you can attach this network to your upstream routers, so this fabric will have upstream connectivity. And the entire leaf spine fabric is controlled by a ONF cluster, and on top of which we run a set of Trellis applications. So why is Trellis so special, and why people should care about Trellis? So first of all, that Trellis is designed according to service provider access and edge requirements. We consider a lot of traffic types and calculation, topology, and ASIC things starting from a service provider requirements perspective. And also, since we're an SDN-based solution, SDN just simplifies and optimizes a lot of existing features. If you want to learn more about how we actually benefit from SDN, please visit the Trellis booth during the expo hours. And then, of course, SDN plus P4 programmable switches just enable new features. There will be an example in CIBA BNG booth demonstrating how we actually use Trellis and a P4 programmable device to do PPPoE termination. And Trellis is an open source solution, which means that the service provider can actually own the code base and have the ability to customize the code according to their need. So one example would be if you visit the Comcast booth, they'll show you how they integrated Trellis into some of their system. So this is just a quick overview of Trellis communities. So for major use cases of Trellis, the first one, and also this is going to be the one you're going to see in the Trellis booth, that this is a very typical service provider network. You're going to have a central office over here where you have a main fabric. You have your VNFs and computes attached to it. Of course, you have your upstream connectivities over here as well. And then you're going to have another field office that's closer to your subscriber, aggregating the traffic in field office. And these will further connect it to different access devices, such as OOT in a PON network, or remote PHY in a cable network, or a base station in a mobile network. And of course, the entire multi-stage fabric are controlled by ONF and Trellis apps. Another example is that Trellis is used in CIBA, which is our broadband access use case. So in this particular example, we replaced the aggregation switch, which is controlled by Trellis, with a Stratum-enabled, P4-enabled device over here. So we actually write a small P4 program and also a small control part on top of it that does the BNG functionality, such as PPPoE termination. This is the one you're going to see in a CIBA BNG booth demo. Another use case is that Trellis can also be used as an enterprise data center fabric. In a typical data center, you're going to have many servers, and you're going to run virtualization such as OpenStack or Kubernetes. They all have their own overlay network. For example, OpenStack has a Neutron plugin, and Kubernetes allows you to write a CNI plugin. And with those plugin, it can actually get integrated with Trellis, so you can have unified control between both your underlay and overlay. And also, Trellis can be considered as a chassis router if you consider a spine as your backplane, and then you can extend this router with adding more leaves that would be similar to your line cards. And also we have a few servers that serve as route processor cards. So this is what we have today with Trellis, and looking forward, these are the things we are recently working on, or we plan to work on. There are a few ongoing things. We keep working on scale and performance improvement, and also hardening the platform. We also have another team working on Stratum P4 integration and the BNG feature I just mentioned, such as PPPoE termination and some QoS functionalities. And there are some other stuff we have several ideas in mind, but haven't started yet. For example, like dual home in the access node, provide in-service software upgrade, and also develop some 5G user plan features. So if you are interested and want to get involved, this is a few ways you can get more information about Trellis. Of course, our website is over here. It just go through a major update today. So if you take a look, there will be new information over there. If you have any questions, feel free to reach out on our mailing list over here or a Slack channel. So I would like to give a probably oversimplified summary of what we have done in last year about Trellis. So this is just a diagram that's showing that in terms of scale, scales in terms of number of routes. So you can see over here that at the beginning of this year, we can only support roughly 10,000 routes here. And then we've gone through several releases, and until today, we can actually support 120K routes. That's roughly 20,000 subscribers. Well, it depends case to case, but we can support 120K routes today. You can see that in a Comcast booth demo as well. So we've been through a lot of improvement in terms of scale in the past few months, and then I actually gave another talk that summarized what we've learned during this process. It's over here, 12 lessons learned from making Trellis production ready. And then some of the talk we're going to have in this track today and tomorrow are also going to touch part of that. So, but I would like to take this opportunity to thank our communities, because without those contributors and our community, we can't really do much like we have today. So I would like to give this stage to Saurav Das, which is the VP of Engineer of ONF, and he would like to give a Trellis Contribution Award.
Thanks, Charles. So we're doing these awards. We're giving out these awards for the first time this year at this ONF Connect. And to be honest, if it were up to me, there would be a lot more people who would be getting this award for going through the journey that we have in Trellis. Okay, so let me give, while we're setting that up, let me give you a bit of a brief history of Trellis. We've been working on Trellis for about 5 years now, actually 4, but before that, a year before that, there was a different project called Spring Open that started developing some of these ideas at ONF for what eventually became Trellis. At that time, I was working very closely with Dell Networking, and we had built ONOS. The first version of ONOS had come out, and so even before that first version of ONOS, there was a closed source version of it that we were developing internally. And as an application that ran on it, we developed this application that would treat a bunch of white box switches. Well, at that time it wasn't white box; it was Dell Networking hardware that we built to make those hardware look like, they would work in any network as a network of segment routed devices. But the people who were working with me at that time, for whatever reason, for different reasons actually, after that 1 year, they all left. And since then, there have been some key moments where some key people have helped Trellis move forward. So the first person that we'd like to actually honor through this contribution award is actually Charles. Charles joined ONF. Charles joined ONF in 2015, and I still remember his first day. He walked in through the door, and before he could sit down at his desk, I went and started talking to him about Trellis. And I feel that he still hasn't had an opportunity to sit down because he's been working so hard on Trellis over the years. So, Thank you for all your contributions, Charles. Okay, so for the longest time, Charles and I were the only two people. No. So Charles and I, for the longest time, we've been working together, and we were the only people working on Trellis until the next person who we want to honor, Nagesh, came into the picture from Comcast. Now, Nagesh and I, Nagesh got interested. We were able to interest Nagesh in Trellis, and over the years, we had a lot of discussions about what features it should include, what it shouldn't, how we should design it, and so on. And he's just been really incredible to even promote Trellis internally in Comcast, and then help us out with requirements and talking about these design and architecture issues. So Nagesh couldn't be here, but in his place, if Lou or could accept this award on Nagesh's behalf. Thank you very much.
I'll take good care of it.
Thank you. Okay, so and then over time, we had more contributors join us. One of the best hires, I keep telling him that he's the best hire that I've made because it's just come at such a critical time that Pierre was able to join us and help us in moving Trellis forward, adding many more features, going through logs. I think Pierre spends all his time with these big glasses that he has. He spends all his time looking at logs. So Pierre, thank you very much for your contributions. It's been great having you on board. So thank you. And then we went into this phase where really without them, Trellis would not be in running in production today. And for that, I cannot thank Hari enough, right? Hari in his calm way explains to us what is broken and how we should be able to fix it. And if Hari was not calm, I think we would not be here today talking about Trellis, right? So Hari deals with so many things, but his demeanor doesn't change. And so thank you very much, Hari, for all for your contributions to our work. Yeah. Thank you so much. And then when it comes to scaling in production, there's some great work. So Trellis is built on top of ONOS. ONOS itself has to scale before Trellis can scale. And there's so much work that has gone in from ONF side and also Infosys side, and in particular, Kali, working with Jordan, it has just, without this effort, Trellis, as Charles mentioned, it scales to 120,000 routes, 20,000 subscribers today. Without Kali's effort, we just wouldn't be there today. So to accept this award on behalf of Kali, thank you very much. And something. And with that, thank you all. And we can start the track presentation. So over to you, Charles.
So let me pull up the slides for the next speaker. Okay, so the next speaker will be Vignesh talking about integrating Trellis into a CarrierGrade NFV platform. Please. You don't have to. Oh, sorry.
Charles. I also have Datta with me. He'll be co-presenting along with me. Hi, everyone. Okay, so this talk is going to be how did we integrate Trellis into a CarrierGrade NFV platform, right? As we kind of move into this world of SDN and NFV, what does CarrierGrade mean, right? So that's kind of changing quite a lot. And this talk essentially is based on our experience at a major telco And we're going to look at all these dimensions and go through really how did we do it, right? So what does CarrierGrade mean in the world of SD and NFV when everything is kind of softwareized? So first thing is really how do we still maintain the high performance, predictable high performance, right? That's the aspect that we're going to look at. Secondly, as we heard in the talks, everything is disaggregated, virtualized, and that comes with its own set of challenges, right? While it really solves a set of problems. So the whole idea is to really look at the Trellis-based solution. How did we make that fully disaggregated, fully virtualized? The next aspect is the scale. Scale is extremely important and probably one of the most challenging challenges that we actually had. We talked about Charles talked about the steps. How did we get to 120K? So we're going to look at how did we how were we able to scale the solution. The other dimension is the HA reliability and fault tolerance. So how did we get that reliability into the overall solution? The other dimension really is the deep real-time visibility, right? So as we actually get into this fully disaggregated kind of mode, getting that visibility into all aspects of the infrastructure and tying that together is a very key component of being able to run the system. So we're going to look at how did we achieve that, and last but not the least, the agile and DevOps, getting the software releases continuously and integrating it into various environments. So we're going to look at all these dimensions. How did we do this, and how did we address these aspects? So just to set the context of the overall solution here, in terms of where does it fit into the overall equation, the use case, or to put this into perspective, we were essentially having Trellis as the backplane switching fabric for a virtualized cable head end, right? So as you see here, the overall initiative really was about you probably would have heard the distributed access architecture, where you're kind of driving more last mile bandwidth in the cable networks. So the idea was really we disaggregate the CMTS, and the DOCSIS MAC and PHY are kind of separated, and you have the remote PHY entity, which really is gives the DOCSIS PHY functions, and the CMTS itself is fully disaggregated, and it runs as containerized functions, right? So in the essentially the CMTS is kind of running on x86 hardware here, general purpose x86 hardware, which is really the switching function in the head end is actually given by Trellis-based solution, right? So as we can see, there's also a control aspect of the solution, which is really where the ONF controllers also runs. So the solution overall, we have looked at all parts of the infrastructure, and pretty much everything is kind of virtualized and disaggregated here, as you can see. So in the same spirit, even the ONF controller itself kind of runs as as a virtualized containers controlled by Kubernetes. So to put things into perspective, this was really the the overall architecture that we had. The one that you see here is the virtualized CCAP cores, which is essentially the virtualized the CMTS entities. For the real-time telemetry standpoint, all elements of the solution was streaming telemetry and logs into AWS, which is the one that really gives us a deep visibility of what's really happening. When Saurabh was mentioning about the logs that Pierre looks at it, this is the infrastructure that really helps us to get all the logs from all part of it, so that you can really analyze to see what really is happening. So so that's the that was the overall context, and please feel free to ask me any questions as we go. So So just to look at from a networking standpoint, what does it really mean, and what kind of requirements was really there. So the first thing really is the fabric underlay itself. So the other thing I forgot to mention is the leaf-spine fabric was completely was a white box based hardware which really runs open flow. It's an open flow controlled infrastructure with the complete control plane running in the ONF Trellis controllers. Just the underlay itself, the underlay networking, which essentially connects the physical hosts. So we do an MPLS segment routing based forwarding across the entire fabric. All IPv6, IPv4, unicast, multicast, everything supported. A MAC VLAN based way of identifying the hosts, and also VLAN cross connect kind of features to support functions which are more L2 kind of functions to the customers, right? So that's the underlay networking part. From a container standpoint, we have multiple networks in the containers. So that's where some of the complexity of our solution really comes in. As you might imagine, most of the data center networks, all your containers and pods are completely handled in the overlay. So we really have a mixture of it. So we kind of use the SRIOV to partition the NIC, and that's directly provided to the containers. So what that really means is, anytime a container comes which has got an SRIOV interface, it actually has it kind of being routed in the underlay. And as controllers, as the containers pop up and goes, it kind of means that it's registering new hosts in the fabric. So that's some of those things which are kind of different from a typical data center style network, and which just kind of adds overall complexity to this solution. As we talked about the MAC and the PHY being separated out. There is a very stringent timing requirements that we need to deliver both to the RFI and the MAC function, which is actually running inside the container in the head end. So we essentially use PTP. You need to make sure that the fabric actually provides without any jitter or latency. The timing messages are provided both to the MAC and the PHY. So that's some of the requirements from a networking standpoint. So the other aspect I wanted to kind of touch upon to give the full perspective of the solution is, as you can see here, the remote PHY is the one which connects the cable modems that you might have. So we actually have like an L2TP v3 tunnel which gets the traffic into the virtualized CCAP entities, and after that it's actually it's into the underlay and goes out to the metro network, right? So there are a number of things that needs to happen to get this to work. Of course, the virtualized the CCAP containers, how do we get that onto the network? That's one part of the aspect. The underlay tunnel establishment, that's another aspect to be taken care of. So all the ARP and ND from all entities that are directly on the underlay will need to be handled, and the DHCP v4 v6 for the end subscribers, as well as some of the infrastructure elements like RFIs will need to be managed by the ONOS control plane. So on successful DHCP transactions, we will have to create routes in the fabric. So this is where some of the scale requirements kinds of comes in. So when we are really talking about 15K, 20K cable modems, it really starts to put in about 120,000 routes, in the fabric. So that's the characteristics of like a end subscriber connectivity. So I just these slides gave a bit of an end-to-end perspective of how Trellis was being used in the solution. So I'll now kind of step into a few things around, the performance and how did we kind of, look at how did we manage some of these. So this gives some of these aspects about the scale and the performance that is that's expected of the solution. So as we spoke about 15K modems needs to start up at one time. So some of the node split kind of activities will require you to really register and get all of them at one shot. So it will really require about 120K routes and 250K flows to be pushed and configured in the system to come up and running. And we have a lot of components, a lot of containers and hosts running. All of them will need to, as their ARP cache expires, they will have to do the ARP to get their gateways, and that's another set of traffic that comes in, and the DHCP of the CMs and the CPs doing DHCP is the other the dimension of the scale that actually comes in. So all of these looks at putting some pressure on the control plane, and we've actually done a lot of things, as what Saurav was also mentioning, a lot of analysis to look at how do we optimize it and how do we make it better, right? So of course the talk tomorrow from Hari, which is going to talk about this in more detail, but at a high level, there are a lot of things based on your particular environment. There are a lot of levers that can be there to play around with, right? So some of it are really timers. So there are timers for the leader election. There are timers for GC. So those are some of the things that we have actually looked at varying so that we can actually get better performance. And we've also done some optimizations which are really very, very particular to our environment, right? So some of it are what we call as route optimization, which is all these endpoint hosts in our particular case only needs to go to one part of the leaves, right? And rest of the leaves that are the leaf switches that are there that don't need any of those routes. So we've actually put in optimization which kind of takes into account that visibility of the topology and makes those specific extensions so that you don't really overburden the system, right, by pushing all these routes and flows to all the switches. The other enhancements that we have looked at is also what we call as symmetric probing, right? So again, because we again take advantage of the fact that we always symmetrically connect our servers, we've kind of optimized the the polling for the hosts on the other switch. So where there is some of these have actually given us quite a lot of advantages and kind of helped us to scale the solution. So going to the next dimension of it, so the disaggregation and the cloud native part. So we have in fact, all our pods are controlled via Kubernetes, and as I talked about, we were kind of architected the ONOS also as a Kubernetes pod. So as you can see, it runs. We either have a 3 or a 5 node cluster, and all the servers are dual connected, and Kubernetes essentially orchestrates if any particular pod were to die. And much of it is completely orchestrated via Ansible, and the entire deployment activity is completely automated. And the other aspect from a networking standpoint, we also have again an SRIOE VF, which is what makes the controller to have a consistent IP address across, so that it can connect to the switches in a consistent manner. So the flannel address, which is the overlay address, that's not used in our case for the ONOS control plane traffic with the switches. So just a few more aspects. Essentially, as I said, we use the stateful set pod, and in a way the ordinality in it will identify which instance, which ONOS instance it is. It has a fixed IP address, and the entire config information is, we kind of store it in a cluster FS, so it's kind of available in any of the servers if the pods were to be moved to a different server. We use a config map to completely automate all configurations that's coming into the ONOS port. So that's how we are. If we lose a particular ONOS pod, we will have another one that comes in. It'll essentially it has all identity standpoint to get the same IP address and get the net configuration. But after that, all the operational state will be synchronized to the new instance. So that's essentially how we kind of make it fault tolerant. So I think I'll take a break here. I'll get my colleague Datta to walk through the remaining components of it, and in the end we can take some questions.
Thanks, Vignesh. So as Vignesh was mentioning, so we are really scaling up to handle around 120,000 routes, which is essentially about 15,000 or 16,000 modems, which also has around 250 to 280,000 flows, which gets pushed at the same time. So we looked at the control plane scaling along with the data plane scaling as well, but there are a lot of things that we had to take care of, right? So for the horizontal scaling, we tried with the 3 to 5 node clustering, which works very well for us. And on the go, we can just go and add the controller nodes, more controller nodes if we need. That's the horizontal scaling part of the control plane. So we have both the configurations ready, and on the go, if we have more number of nodes added, we can just get that done. And there are a lot of while we were scaling up for these things, the distributed store of ONOS was one of the issues actually, where we had to ensure that the backup of some of the flows doesn't happen at the same time when the things are scaling up. Because when we have a large number of devices, everything has to be provisioned or the flows has to be programmed at the same point of time. So we had to set in a lot of timers and ensure that it doesn't really bring down the system. So a lot of optimization techniques and things have been gone there as well. Hari will be touching upon some of those things in the optimization and fine-tuning stuff tomorrow. So at the same time, seamless path computation on data path scaling. This is like we have a setup where we keep on adding the remote PHY nodes, or we keep on adding the cable modems on the go. The way we do it is in our lab, we have the systems. We simulate certain sections of the network, our live network. But we say that we want to add more nodes or more customer to that. We will add up a switch as well. We can add a leaf. We can add more RPDs behind it on the go. We add up thousands of cable modems behind that on the go, and we see how does it scale, basically. Right? How does the ONOS as a controller can take it up? How does it behave? So we have fine-tuned some of the memory stuff there. There were some of the threading issues which we had fixed over there with the help from Charles and the team. So a lot of such things have been handled on the control plane. And there are fine-grained OF filters, packaging filters to handle the control plane storms. When I say that when we bring up a lot of these devices, there are a lot of ARP packets, DHCP or ND packets that come in. And that storm used to bring the system down in the beginning. So we had fine-tuned them. We had to get it into a thread pool model and then throttle them. So we have handled all those things. Probably that will be covered again in tomorrow's session. So coming up to data plane, as I said, it's a very volatile and dynamic network. So we keep on adding these nodes, what are called remote PHY nodes on the go. So we need to ensure that we have programmed additional stuff to ensure that these flows just get added in. And once you add the R5 node, everything is dynamically within the network, and you can just keep adding the customers without bringing the network down or without affecting the customers that are getting added newly. And then, so in this, if you see, okay, I'll use this, sorry. So here we use something called aggregator switches. This is, this is something which is slightly new in the concept of Trellis. So other than the leaf spine, this is another pair of spine kind of thing, where all our end leaves, which we call DAS, where the R5s go and aggregate, they terminate onto this aggregator switch. And then it just connects the spine in our central office. So we have a fiber running between them, which means we can add more number of such leaves behind them. At the same time, we can add more number of customers on the go. So this slightly alters the leaf spine architecture, but then we did well to get that out of our way, and it's working pretty fine for us now. But this is just a slight change in our architecture, the way we look at the leaf spine or trellis fabric as such. It's a modification to that. So the rest of the things, as I explained, scaling of CM behind the RPDs on the fly, we definitely have to do that and bring up more cable modems and components on the go. So this is some of the scale stuff that we have done. And on the HA side, we have all our servers dual homed, basically. They are connected to two leaves at the same time. And those two leaves also have a pair link for the failure. If you look at this, so if especially on the downstream, if one of the switch fails, it always transfers the packet coming on to any of the hosts connected there onto the other switch for the downstream packet. So downstream packet. So it always gets delivered without miss. So we have multiple ECMP links, and we also have the dual connections to our spines instead of one. All the leaves do have dual connections to all the spines that they are connected to, and it's a fully connected ECMP network, basically. So and then along with the servers, we also have the containers, basically, which is our VCAP or VCMTS workload. So in our case, there will be one VCMTS per R5. So there will be hundreds or thousands of such Docker containers running on our servers. And when one of the container goes down or it moves across, it was real pain for us to reprogram all the switches at the same time. So what we did was we changed the logic in which L3 to L2 flows gets programmed, L3 interface to L2 layer programming. So we are just changing, instead of rewriting the complete next objective at the end layer, we're just pointing to the different L2 group. That means it's just one switch without affecting anything. That's at the flow programming layer, basically. So that's what the route reprogramming for pod HA talks about. So which means when we really have a new pod coming up or a pod dying down on one server coming up on a new server, we just have to change one link. That's the last leg of the flow instead of changing or reprogramming the complete flow. That's an advantageous thing for us. And on the switch side also, to ensure that we have connectivity, we have active-active Linux bonding, which is also supported by the ONF controller when we have active-active bonding. So we ensure that we have the Linux bonding on the server side. Also our SROVs are bonded as well. We have a bonded VFs on the containers as well, so that if one of them goes down, we have the redundancy and we can still continue to work. So these are some of the HA stuff that we have taken care of on the data path of our network. So moving next, we slightly touched upon this. So these are the basic criteria of the SDN, where switches simultaneously connects to the multiple control instances when we have the cluster. So it ensures that if one of the controller goes down, if master goes down, the backup picks it up, and it just ensures that the switches are intact and the data path is intact. But at the same time, the ONOS controllers, which are really Kubernetes pods, are brought up by the Kubernetes. It ensures that the pod comes up, rejoins the cluster without any issues. We have set it up as a stateful set. And along with it, we also have the config maps where we just put down the net config configuration with the net config. So which means when the pod comes up, the configuration which was already available is pushed down into the new ONOS controller as well, and it seamlessly joins the cluster. So within few seconds to a minute or so, the new container is up and running without bringing down the data path, without affecting any of the thing on the data path. So this has been tested out and it's working out pretty well for us. So losing ONOS instance redistributes switch master chip. Again, I talked about it. So if one of the masters goes down, the master chip is taken out by one of the other instances. So clusterFS is the volume where we store our config maps. This is part of the Kubernetes construct again. We have a local mount using the clusterFS, the file system that we use to mount onto our Dockers, and we store the config maps over there. So once it goes down, once the Docker container gets restarted, these things are readily available on the Docker disk, basically the mount. So it just picks stuff from there. We have automated Ansible scripts to ensure that these things are pulled in, and then they get triggered, and the configs are pushed in to the new instance that just came up. So we have the redundancy of server hardware, the network connectivity, and the storage, as I talked about, all across the controller part. So with this, we were able to get all the required scale. We were able to achieve a very good redundancy all across, and we are able to get the system up and running for a long time, actually, even when we are scaling up. So some more things on the scalability and the reliability aspects. We still had a couple of things to take care of on the JVM side, the memory that we really fix when the controller comes up. That's one aspect, probably will be touched upon by Hari tomorrow. And the kind of garbage control algorithms that we use, the parameters that we pass on to that, along with the LLDP timers, a lot of other timers we had to play around with. So most of those things which we are not touching upon here today will be touched upon by Hari tomorrow in detail. So this is our, getting on to the next one, this is our telemetry component, basically. What we have done here is, so we have gone ahead and written a sidecar to the ONOS, which is called ONOS Exporter. And we also have a lot of REST APIs implemented within the ONOS for all the metrics that we need from the ONOS, including the current status, the flow stats, the route stats, all the required FM information and all the things. So this ONOS Exporter is a sidecar which runs along with the ONOS container in the same pod, but it just does some API calls periodically to collect the information from ONOS, to get the health information, to get the metrics, to get the event-related information. It extracts every other required information from the ONOS. At the same time, we also have OM, which is the optical monitoring tool, on our switches, and we also have Redfish API put on the switches, basically. And we have integrated the control part of it within ONOS pod, and that gets the information of our fabric. It gets the information of the SFPs, it gets the temperature on the switch, all the fan status, all the required stuff that's from the hardware, and along with the CPU utilization of the switch, the memory that's being used on the switch, all the required information is obtained from the switch. And then we aggregate all of them, and we passed on to something called platform monitoring probe. Monitoring probe is our custom app again, which aggregates all these things, and it opens up, it has connectivity to the Kafka bus that we have actually. So it handles the Kafka bus, and it creates a topic for all these details that we have obtained and puts it onto the Kafka bus. So once it's on the Kafka bus, it reaches our Prometheus server. Basically, we have consumers on the Prometheus side, which just pulls the data out of the Kafka and puts it onto Prometheus. And we have created a lot of dashboards from Grafana using the data in the Prometheus. So this is kind of a single pane of glass for all our ops guys. And we also have alerting mechanism based on the information that we obtain from Prometheus. And other thing that we have not shown here is the EFK bus that we have. Basically, for all our logging, we have the Elasticsearch where we store all our logs and we create dashboards out of it. So our alerting system is two-pronged. One, it uses the data from the Prometheus, which is more event-based, and it also uses data from the Elasticsearch, which is more from the log-based. So based on this, if there are predefined kind of alarms, if this happens, okay, alert it as CV1, serve1, serve2, serve3 kind of alarm. So it sends the alarm to our ops guys to ensure that they are aware of it and they can take care of it. Though we have built-in mechanisms. We just inform them to ensure that the things are taken care. So this is the architecture we have on the telemetry side, which is which gives us more visibility into the system. And these are some of the dashboards and the information that we really have put together. So this one has switch-related information, basically how many switches are connected, what are the status, all the node status of the ONOS cluster, all those things are being replicated over there. And some of the things have JVM information, the CPU information. This also has the information of the servers which are hosting the ONOS controller itself, along with the switch information. So we get all this information, and this is our logging system, basically Elasticsearch, and we have dashboards created out of this. And if there's any other thing, we have created a dashboard which gives us important occurrences of events, which also triggers alarm to our operations. So moving ahead, this is the last piece of the thing that is straightforward one, basically where we have our CCD pipeline. So we are predominantly doing everything through the Jenkins build job, and so this is the continuous integration, continuous deployment, but I'll just try to cover it in a go where whenever there's a new release on the ONF Git, we just mirror it out in our local Git. So there's a cron job that runs, Jenkins job that runs every night to ensure that our Git is in sync with ONF Git. And from there, there'll be master branch created whenever there's a new requirement, whenever there's new custom app that we need to do, or some other enhancement that we need to do. We'll have a custom branch, master branch created, and that'll be from there, the user, the developer, whoever is doing the changes will branch out and will do the code changes and push it in. Once that is reviewed and approved, so that push will be pushed forward, and there'll be pull request into the system where our Jenkins job will get triggered. It picks the whole code base, it builds the thing, and then it also containerizes it. We have the pod spec, as Vignesh was explaining, we have the Docker spec and the Kubernetes spec. So it just builds the complete container, and then it deploys it on one of our test network where we have automated a lot of things on the Teston framework. We are using Teston as an automation tool. And we have around 150 test cases as of now, covering all the switch level HA, controller level HA, multicast applications, and a lot of things which gets tested. We have a basic sanity package of 50 test case, suite of 50 test cases, which is in the Teston. So that gets triggered in. Once it passes through that information, the whole container, which has the upgraded ONOS, will be pushed onto our Nexus, basically. And from Nexus, whenever we need, it's a manual job to trigger the pull. So it pulls from the Nexus, and we have the Ansible. We have the Ansible scripts which can really go and push it and deploy it on the required environment. We have around 8 to 9 lab environments where we do system testing, scale testing, integration, dev testing, a lot of different tests, and we have predetermined or pre-marked environments for each of these things. So we specify where do we need this, and accordingly it's going to label the build, and it will be pushed in, and it will bring up the whole system end to end, which is a tested one. And if there are any issues when it's running the automation, we do get the alarm, and we can the developer can go and check it out and correct it and repush it back. So this is our CCD pipeline overall, and this is how it basically works, what I was explaining. So there's a cron job, and CCD team does a lot of the things. It set up a release tag, and Jenkins starts the build. If there's anything, it will also notify the designer in between while running the automation, or even before that. So this gives a high-level view of how our CI/CD, the complete pipeline, is being handled. So we also have the customer apps. We have the things that we get from ONF Git directly. We have the customer apps, and also we have all the Docker spec, bot spec for the Kubernetes, all those things which we are handling it by ourselves. So that's the thing that we had for today. Any questions we can take?
So just wanted to ask a couple of questions, actually. So in the link resiliency slide that you showed, so the reason for having dual links for each leaf to spine connection, and to have the two leaves with a leaf-to-leaf connection was due to the availability requirements of the CCAP of the workloads, or what was the choice behind this?
So yes, one is the availability requirement, of course, but we need to. So if by any chance we lose one of the links, not because of the control issue, but because of any other SFP issue or any other thing, it happens in our labs as well. So we wanted to be on the safer side, ensure that if one is not there, we have the same connectivity going along on the other one. So we just.
Sorry, is the question why do we have link between the two
Dual links. Leaf and spine.
So, and also, why do you have the leaf-to-leaf pairing link?
Okay. So the dual link from leaf to spine is just link redundancy.
Link redundancy.
Okay. Yeah.
Gives you more redundancy. It's a level of redundancy that you want to have. But the connection between the two leaf switches is the architecture in Trellis, and it's more done to kind of limit the impact of anyone changing from you to really impacting the rest of the cluster. Because any downstream traffic, right, the rest of the cluster does not need to worry about it. So it will still be sending wherever it sends, and it will use the leaf-to-leaf pair to then divert through that. So that's just to limit the amount of changes that you're making to the entire fabric.
Okay.
Right? Of course, Trellis. Saurav can explain that better than me. So,
So the dual links for redundancy, yes, but also for faster recovery, because what happens is the Broadcom chipsets that are inside those leaves and spines, they realize faster than the controller does, because first the hardware has to realize it, then the controller has to realize. So by the time the controller comes in, and then that also happens fast, but recovery here, if you do dual links, it can happen at hardware speeds, because the hardware itself takes out one of the links from the ECMP groups that you see over there, right? And then the controller will come in and do its job, but just hardware speeds, you get faster recovery by having dual links between the leaf and spine. And the link between the leaves, that helps with what Vignesh was explaining. It was about local recovery, right? So imagine those two leaves that are paired to each other. They're connected to, say, 48 servers, okay? And if you lose one of the servers, right, every other part of the fabric can still reach the rest of the servers through both of them, right? But it's only one of them that is not able to reach because you've lost one of the links. So that pair link then takes the traffic for only that particular server through that local recovery. You don't have to change, programming everywhere else in the network. Everywhere else in the network thinks, okay, that's just fine. I'm just going to send my traffic to both of them. But locally, we handle this failure of one of these guys.
So it's to reduce churn
in the network, yeah.
And sorry, I had a second question.
Yeah.
So the VCCAP are all containerized,
they're all
or
containerized.
virtual machine containerized.
They're all containerized. In fact, we all have bare metal containers. There is actually no VMs in this whole solution at all. It's just bare metal containers.
How different do you think it would be integrating with a VM environment, like an OpenStack environment, for example?
It wouldn't be different from a networking standpoint. But from a networking standpoint, even for the VMs, we can actually have SRIOV, and we can make sure that the VMs actually are getting an address in the fabric, because we cannot afford to actually go through the hypervisor and go through the overlay especially for your DOCSIS user plane traffic.
Yeah.
So that's cannot be possible. So we need to be able to bypass all those stuff. And in fact, because we use DPDK there, it also bypasses completely the kernel interface.
Agreed.
So that's it's exactly the same. The way we would orchestrate in the VM would change, but from a Trellis standpoint, doesn't change. So we'll be able to handle it in the VM or in the container. Exactly.
And do you have to integrate on the Neutron API with, say, OpenStack, or
if we are doing the
so you have to assume that you are deploying your OpenStack cluster as you deploy your Trellis fabric, so you can integrate, say, replacing a legacy fabric with Trellis on an existing OpenStack deployment.
That's right. Yeah.
Okay. Understood.
In fact, the Sona component of of Trellis actually supports the overlay. It implements Neutron APIs and
That's right. There's another project at the ONF called Sona that came in from
SK Telecom.
SK Telecom. That's right. And SK Telecom actually has that deployed in production as well. Sona is a faithful implementation of the Neutron APIs. So in principle, you could use Sona as an overlay and work with Trellis as an underlay.
And recently, I also started a new project called Sona CNI. It's very similar to the Neutron work, but it worked with containerized environment and Kubernetes CNI.
Because one of the reasons I was asking is because oftentimes, like, you have to also fight with your potentially OpenStack provider to be able to support different networking backends and different fabric integrations. So if you can do it, say, on a not on the Neutron API, but on the OpenStack API, let's say, after the fact, that makes it a bit easier in terms of segregating instead of having to tightly couple everything together.
I would say using Trellis with other overlay network, it actually makes your life easier because if you use traditional underlay fabric, you basically have very few control over it. It basically just provides you L3 connectivity and maybe a few tunneling things. But with Trellis, you actually have a lot of, you can manage both underlay and overlay and own their control. So there's actually more flexibility over there. All right, we're running out of time, so maybe just one more question if there's any.
Questions? Thank you so much. Thanks, everyone.